Force acting on current-carrying conductor in a magnetic field. Let us perform an activity to understand this concept. The apparatus required to perform this activity are a thin flexible copper wire, 2 electric cells, a horseshoe magnet having a strong magnetic field, a plug key, connecting wires and a stand. Let us now connect the circuit. First, we shall fix the thin flexible copper wire using a stand. Now connect the upper end of the wire to the battery. Connect the lower end of the copper wire to one end of the plug key. Then we shall connect the battery to the other end of the plug key. Always remember to keep the key open while making connections between apparatus. First, we shall take a horseshoe magnet. Let us hold it in such a way that the copper wire is between the poles of the horseshoe magnet. What do we observe? We do not see any movement in the copper wire. This indicates that whenever a current is not flowing through the wire, it remains straight. Let us mark this position of wire as A. Now, close the key and allow the current to flow in the circuit. Let us observe the copper wire. Do we see any movement in the wire? Yes. When the current flows from top end of the wire to its bottom end, the wire bends. Let us mark this position of wire as C. Let us now keep the plug key open. We observe that the copper wire becomes straight again. That is, it again comes back to position A. Now change the direction of current flowing through the wire by reversing the connections. That means now the current is flowing from the bottom end of the copper wire to the top end of the copper wire. Close the key. What change do we observe in the position of the wire? This time also the wire bends, but it deflects to the opposite side of the position C. Let us mark this position of wire as B. Bending of copper wire when placed in the magnetic field is possible only when the force is exerted on it. Thus, from this activity we can conclude that whenever current flows through a conductor in the presence of magnetic field, a force is exerted on the conductor. If we take the directions of magnetic field, direction of electric current, and that of the force on the wire, then we come to know that the direction of the force on the wire is perpendicular to both the magnetic field and the direction of the current. In the previous activity, we have seen that when the direction of the current is reversed, the direction of the force also gets reversed. This means that the direction of the force depends on both the direction of the current and the direction of the magnetic field. Now can you tell what will happen if the magnet is kept reversed? That is, what will happen when the direction of the magnetic field is reversed? When the current flows from top end of the wire to its bottom end, and if the direction of the magnetic field is reversed by reversing the poles of the magnet, then the wire bends to the position B. That means, even after interchanging the poles of the magnet, the direction of the force of copper wire is reversed. Let us now answer one more question related to this concept. Experimentally, it is possible to show that the force on the conductor is maximum when the direction of the current is perpendicular to the direction of the magnetic field. How can we do this? Come, let us understand. First, we shall arrange the apparatus as shown here. Let us keep the wire in between the two bar magnets as shown here. That means the magnetic field is perpendicular to the position of the wire. Now, allow the current to pass through the wire. We can see that the wire gets lifted upwards. Now let us keep the wire at an angle to the magnetic field. What do we observe? We see that the wire gets lifted upwards this time also. But the extent to which it gets lifted is less as compared to that in the case when it is kept perpendicular to the magnetic field. Now let us keep the wire parallel to the magnetic field. Do you see any change in the position of the wire? No. The wire does not deflect from its position. That means no force acts on a current-carrying conductor when it is parallel to the magnetic field. This showed that the deflection of the conductor is maximum when the conductor is kept perpendicular to the magnetic field. If the direction of the current in a conductor and the direction of magnetic field are known, then the direction of force acting on the current-carrying conductor can be found out by using Fleming's left-hand rule. Come, let us study this rule. Fleming's left-hand rule. When a current-carrying conductor is placed in a magnetic field, a force is exerted on the conductor. There is a simple rule to determine the direction of force acting on a current-carrying conductor placed in a magnetic field. This rule is called Fleming's left-hand rule. According to this rule, the left-hand thumb, index finger, and the middle finger are stretched so as to be perpendicular to each other. If the index finger is in the direction of the magnetic field and the middle finger points in the direction of the current, then the direction of the thumb is the direction of the force on the conductor. Come, let us now verify this rule by performing an activity. Activity. Consider the same setup shown in the earlier activity. Let us now determine the direction of force on the wire using Fleming's left-hand rule. Here, we are using vertical current-carrying conductor placed in a magnetic field. The direction of magnetic field is from north to south. The direction of current is vertically downwards. We can see the conductor getting deflected towards the position C. Now let us verify the direction of force by using Fleming's left-hand rule. Let us stretch our left hand so that the forefinger, center finger, and the thumb are perpendicular to one another. Now the forefinger is pointing from north to south, that is in the direction of the magnetic field. The center finger is pointing downwards, that is in the direction of an electric current. Now look at the direction of our thumb. The thumb is pointing towards the position C. This gives the direction of force acting on the wire. Similarly, we can verify the direction of force on the wire kept in magnetic field when the current is flowing in the upward direction through the wire. In this way, the direction of force acting on the conductor can be verified using Fleming's left-hand rule. Come, let us now proceed further.